Hello, we're Phoenix Aerospace, and today we'll be telling you about our final presentation for the Solar Satellite UAV. But first, let's meet the team. To begin, I'm Ryan Breisch, I'm the team lead.
I'm Tyler Wilhite, I'm the configurator.
I'm Jared Hinckley, I'm the capture manager.
I'm Haley Wilson, I'm head of CAD and graphics.
I'm Carson Campbell, I'm head of aerodynamics and control.
I'm Anthony Pascal, and I'm head of propulsion and power.
I'm Boone Miller, and I'm the lead of weights and structures.
I'm Caleb Besmer, and I'm the lead of system avionics and ground support.
So to begin, our mission requirements that we had were we needed to create a solar UAV that has a TAMDAR sensor, an FMV camera, and a still camera. It needed to be GPS with autopilot and take off and land on a runway of 9,000 feet. It needed to be able to fly in 30-knot winds with 50-knot gusts, all while using technology that was going to be ready by 2029 and be comparable or better than the technology that exists today. This is the aircraft that we came up with. We named it the Icon J. The flight profile and ConOps for this aircraft, it's going to take off and land at 5,000 feet of elevation, climb up to 60,000 feet, which is its cruise velocity, and then land once a year for maintenance. This is the schedule that we used going forward for our project.
When designing the wing, we had a couple things in mind. We wanted to be capable of flight at low speeds and have a planform that produced minimal drag while also producing sufficient lift. Now, to start the design process, we first had to select an airfoil. And we know we needed an airfoil with a high lift to drag ratio, and after comparing several, we finally landed on the Epler E216. And for the size of our wing, we compared that to our benchmark aircraft. And for a high altitude, long endurance aircraft, high aspect ratio and wing loading values were very common. So to satisfy these, we selected a wingspan of 200 feet and an average chord of 6 feet, which aligns very well with our benchmarked aircraft. Now for our wing planform, we wanted an elliptical lift distribution, but without the elliptical planform, as to avoid the stalling issues associated with this planform. This led us to design a tapered and swept wing planform with a root chord of 7 feet, a tip chord of 5 feet, and a sweep of 3 degrees. Now, we also needed high lift devices to assist in the takeoff and landing sequences of flight. Trailing edge flaps were placed on the innermost section in between both the fuselages, and ailerons on the outer 25 feet of the wing to assist in control during flight and to also assist the flaps whenever necessary.
The goal for propulsion team was to have continuous flight using electric motors and solar panels, with an optional goal of running in 50-knot wind. The first step was deciding the motor. We had 3 choices for our motor. They were a lightweight motor with low power output, a medium weight motor with medium output, and a heavyweight motor with high output. The most valuable category for our decision matrix was weight, and that is why the Hex HPDM 250 motor won. Then we had to decide our propeller. We had 3 choices for our propellers. We had a long 3-blade, we had short 12-blade fan, and then we had a medium 3-blade. The most important category for us was efficiency on this, and due to its high efficiency, the 3-blade long won. Our propulsion system came down to that 2 hex motors and 366 pounds of lithium oxygen batteries due to its high energy density of 1750 watt hours per kilogram, and a wing covered by solar cells of 6J IMM, which produced a total power at peak of 43.7 kilowatts. And lastly, 2 long blade propellers with a radius of 3.94 each.
All right, so our goal for weights and structures was to design a structure for our aircraft that was both light enough and strong enough to overcome any structural loadings that our aircraft would experience. And we also needed to maintain it being cost effective and manufacturable. Alright, so our design concept features carbon fiber for internal components such as ribs, stringers, spar, and as well as ring structures for the fuselage. So basically any internal structural component will be carbon fiber. We have selected aluminum 2024 T3 alloy for the skin of the wings and fuselage, and then titanium will be the main structural component for the landing gear. Alright, so when we were designing ribs for our aircraft, we had two main design competitors, and so one involved triangular cutouts for the rib and the other one involved circular cutouts for the rib. Ultimately we went with the triangular cutout because it shaved more weight off of our rib design. And then here is the kind of the wing tip of our aircraft with the internal structure layout. You can see our ribs and you can see our spar running across, and we will have stringers running across as well. Here's the structural layout for the entire aircraft. You can see the ribs and spar for the main wing, and you can see the ring structures for the fuselage and the stringers running across the fuselage, and then the tail internal structure, which again follows a similar format to the main wing.
For system avionics, the goal was to make continuous and persistent atmospheric observations at 60,000 feet where we're at cruise. We required a TAMDAR sensor, an FMV high-resolution camera, and a GPS autopilot with an optional high-still camera. The TAMDAR sensor given in the RFP is a very efficient sensor that measures humidity, pressure, winds, turbulence, among other things, and sends the data back to the ground via satellite. The defroster chosen is the thermowing, and the great thing about it is it can be fitted and sculpted to the wing as well as the propeller blades and can fit whatever size we had designed it as, and it will rapidly remove ice off the wing anytime it drops below 41 degrees Fahrenheit. When selecting a camera, we decided a gimbal would be the most efficient because it can act as the FMV camera and the high still resolution camera. It's weathered seal with 360 degrees rotation and anti-fog features, and it has full HD photos and videos. The transponder autopilot we selected from Trig has a ETSO certified GPS with altimeter and a built-in altitude encoder, and it functions up to 70,000 feet well above our cruise, and has an attached receiver kit with an antenna to send all of the data into the controls from the ground. Here's our final avionics configuration. As you can see, the defroster is evenly placed across the wing and propeller blades, with both cameras being above and below the middle of the wing, and the sensor and autopilot in opposite fuselages, making our total payload just above 55 pounds.
So that was the aircraft that we had designed. However, if we were going to put it into use in the real world, there's some things I would want to do first. The first thing we would want to do is research connecting the two horizontal stabilizers to allow us to have increased rigidity and an overall greater strength of the aircraft. Second thing we want to do is we want to look at more propulsion systems and make sure that everything is as efficient and as powerful as it should be given real world conditions. The third thing we want to do is do a complete structural analysis of the aircraft to make sure that it is going to uphold its composure over the stresses and strains of aircraft flight. The fourth thing we'd want to do is optimize fuselage placement to make sure that we had the optimal center of gravity and it was as stable as possible for the aircraft. The last thing that we'd want to do is we'd want to design more configurations of the aircraft to allow us to have a greater marketability. With that being said, thanks for watching. Go Pokes.